Welcome to our guide on mastering data functions in EViews. This presentation will cover the essential techniques for data creation, transformation, and simulation. We will explore how to manipulate time series data and use statistical functions to prepare your data for robust econometric analysis. For instance, before running a regression on GDP and consumption, you might need to take the logarithm of both series to stabilize their variance and interpret the results as elasticities. So why is this data preparation so crucial? Let's look at the common challenges we face with raw econometric data. Raw economic data rarely arrives in a format that's immediately suitable for econometric models. As you can see on the left, it often exhibits issues like non-stationarity, meaning its statistical properties change over time, scale disparity, and pronounced seasonality, which can obscure underlying trends. These characteristics frequently violate the fundamental assumptions of ordinary least squares, or OLS, regressions, specifically linearity, homoskedasticity, and normality. If we use raw data that violates these assumptions, our model's inferences can be misleading or invalid. The good news is that EViews provides a powerful set of data functions, depicted as a funnel in the center. Functions like log for linearization, d for differencing to achieve stationarity, and @cs for seasonal adjustment allow us to rapidly transform this raw data. The goal is to produce model-ready data, which is stationary, linearized, and exhibits normal homoskedastic properties, enabling valid and reliable statistical inference. This decision map outlines a strategic workflow for data transformation. It's crucial to avoid applying functions randomly. Instead, you must first diagnose the properties of your data, looking for issues like trends, seasonality, or outliers. Begin by importing your data. Then, check for stationarity. If the data is not stationary, apply time series functions, such as differencing, d, or log differencing, dlog. Next, assess if the data's scale is too large. If so, apply mathematical functions like logarithm, log, or square root, sqr. Finally, if your objective requires simulation, use random generators like rand or nrand. Once these steps are complete, you can proceed to output, estimation, and modeling. This systematic approach ensures you select the correct EViews function to address each specific data issue effectively. EViews functions can be grouped into three main categories. First, time series transformations, which include lags, differences, and growth rates, are the backbone of dynamic modeling. Second, descriptive and mathematical functions, like logarithms and moving averages, help with scaling and smoothing data. Third, stochastic and random functions are used for simulations, such as Monte Carlo analysis, by generating random numbers from various distributions. A key distinction in EViews is between functions that operate row by row, like log of x, and those that summarize an entire column, like @mean of x, which returns a single value for the whole series. To create a new variable, log GDP, you would use the row-specific function, log of GDP. To demean the series, you would use the column-specific function in the expression GDP minus @mean of GDP. Let's begin by looking more closely at the mathematical and descriptive functions and their syntax. The core syntax for creating a new variable in EViews is straightforward. Series, new var, equals expression. The natural log, log of x, is fundamental for converting levels into percentage changes and for modeling elasticities. The @mean of x function calculates the average of a series. While it returns a single scalar value, EViews fills the entire new series with this value to facilitate further calculations, like demeaning a variable. Other useful functions include @moveAv of x, n for smoothing data by calculating an n-period moving average, and @trend for creating a simple time trend variable, often used to capture deterministic trends in a regression. The big three time series functions are essential. First, lags, denoted as x-1, represent the value of the variable in the previous period. They are the building blocks of autoregressive, or AR, models. Second, differences, Using the d of x function, calculate the change from the previous period, as in x of t minus x of t minus 1. This is the most common method to achieve stationarity. Third, growth rates. While at PCH of x gives the exact percentage change, d log of x calculates the log difference. In financial econometrics, d log of x is often preferred because log differences are symmetric, additive, and statistically more tractable for asset returns. Random number generators are essential for advanced techniques like Monte Carlo simulations, bootstrapping, and stress testing models. EViews provides two main functions. RND generates random numbers from a uniform distribution between 0 and 1, while NRND generates them from a standard normal distribution, n, 0, 1. To generate numbers from a normal distribution with a specific mean, mu, and standard deviation, sigma, you can use the transformation series x equals mu plus sigma times NRND. Crucially, these are pseudo-random numbers. To ensure your simulation results are replicatable, always set a starting seed using the RND seed command before generating the data. This guarantees that anyone running your code will get the exact same sequence of random numbers, as shown in the example RND seed 1, 2, 3, 4, 5. The Gen button on the workfile toolbar is the fastest way to access the equation dialog. You don't always need the full menu path. The Generate Series window is where you define your transformation. In the Enter Equation box, you type the expression, like log GDP equals log of GDP. A very powerful feature is the Sample Restriction box. This allows you to control the scope of your calculation. You can restrict the transformation to a specific time period, for example, by typing @all 1990-2020 to apply it only to data from 1990 to 2020. You can also apply conditional logic. For instance, using an if condition like if GDP greater than 1,000 would perform the calculation only for observations where GDP exceeds 1,000. This slide demonstrates how to effectively work with groups in EViews, especially for validating data transformations. The process involves 3 simple steps. First, you select multiple series, such as your original data and its transformed version, by holding Control and clicking on each series. Second, you right-click on the selected series and choose the Open as Group option. Finally, this action will open a spreadsheet view where both your raw and transformed series are displayed side by side. The validation section on the right emphasizes the importance of this process. Always open your new series in a group with the original. This allows you to visually verify that the transformation aligns with your expectations before you proceed with any modeling. This crucial step helps prevent errors and ensures the integrity of your analysis. Let's start our case study. Our task is to analyze the volatility of the GDP growth rate, but we begin with raw nominal GDP data. The first step is always to load the data, and then, crucially, to inspect it visually. Never start modeling blind. We can do this in EViews by going to View, Graph, Line. The resulting chart of raw nominal GDP clearly shows a strong upward trend. This visual pattern is a classic sign of a non-stationary series. Running a regression directly on this data would likely produce spurious results, meaning we might find a statistically significant relationship that is actually meaningless. The graph shows GDP starting near 0 and growing exponentially to over 20,000. This is a clear indication of a unit root process, which must be addressed before modeling. Now that we've diagnosed the problem of non-stationarity, the next step is to apply a transformation. This slide focuses on transforming non-stationary trends into stationary growth, a crucial step in econometric analysis. We explore 2 primary methods for calculating growth rates. Block A illustrates using @PCH GDP for the exact percentage change. This approach is generally easier to explain to a non-technical audience. Block B presents the log difference method. DL GDP equals D log GDP. As indicated by the Best Practice section, D log is the preferred standard for econometric modeling. Although @PCH might be simpler for laypeople, D-log is favored by practitioners due to its inherent mathematical symmetry and better statistical properties, which are vital for robust analysis. The table provided shows a series of values for DL/GDP as an example of the output from this transformation.
This slide focuses on simulating a supply shock to stress test an economy. We generate a shock using the command series shock equals 0.5 times NRND in block A, which introduces random noise from a standard normal distribution. Then, in block B, we apply this shock to our GDP growth path with series GDP sim equals GDP growth plus shock. This process is part of Monte Carlo analysis, where we inject noise using NRND, normal random, into the data to assess how sensitive our models are to random volatility. The table shows an example of observed shock values and their impact on the simulated GDP.
The descriptive statistics table is your primary diagnostic tool. It quantifies exactly how your transformations or simulations altered the data's distribution. The final step is to formally confirm that our transformed data is now model-ready, meaning it is stationary. We use a unit root test, such as the augmented Dickey-Fuller test. The null hypothesis of this test is that the series has a unit root. It is non-stationary. We are looking for evidence to reject this null. The key output is the p-value. A p-value less than a significance level, typically 0.05, allows us to reject the null hypothesis. In our results, the p-value is 0.0021, which is much less than 0.05. Therefore, we reject the null and conclude that our data is stationary. This process is circular. We diagnose, transform, and then test. If the test had failed, we might need to apply another transformation, such as a second difference, d of x2. This slide provides a handy syntax cheat sheet and additional resources for EViews functions. The table outlines key functions such as d of x for first differences, d of x, n